All right, so we've been looking at enols and enolates. These are reactive intermediates that are made from carbonyls, and it's a really powerful thing because we normally think of carbonyls as being electrophilic at the carbonyl carbon. However, once an enol or an enolate is formed, we actually flip the script. We actually wind up making nucleophilic character at the alpha carbon. And we've just started looking at some of the actual reactions involved. We started off by looking at using halogens as electrophiles. We started off with the alpha-halogenation under acidic conditions, and it proceeds through an enol as a nucleophile, reacts with a bromine or a chlorine, whatever, and typically gives you a monohalogenated product, simply replacing one of the alpha hydrogens with a halogen. Now, under basic conditions, there's an implied excess of the halogen, and what happens is something called exhaustive halogenation, where all of the alpha protons are removed and replaced with halogens. So you can control the outcome of the reaction based on how the conditions are, basic or acidic. So next we're going to look at a couple of spin-offs of this chemistry, starting off with the haloform reaction. And you'll note that I have actually started with a slightly different reactant than I did in the previous reaction. In fact, if you look at the conditions, we simply have an excess of halogen and base again. It looks very similar. Now, the difference here is that this is a methyl ketone, and that's imperative for the haloform reaction to work. The reaction proceeds through an exhaustive halogenation under basic conditions, replacing all three of the alpha hydrogens with, in this case, bromines. Now, at that point, this is a ketone, right? And it actually doesn't behave exactly like a ketone. This trihalogenated compound actually acts more like an acid derivative and undergoes an acyl substitution with hydroxide as the nucleophile. And again, this should remind you a lot of what we talked about before when we looked at carboxylic acids and how quirky they are, in that they're actually less reactive than they ought to be because of that thermodynamic sink that's involved. So when you look at this reaction, hydroxide can attack the carbonyl, break the pi bond, which then reforms, and can now expel either the hydroxide that just attacked or CBr3 minus. Now, certainly the hydroxide is the better leaving group, and it would usually just fall back to the starting point. But remember, energetically, while that's favorable, a small amount of that carbanion can in fact be expelled. And the only reason that's even remotely possible is because you have those three halogens attached, creating an inductive effect, stabilizing the negative charge. So once the hydroxide attacks, it can displace this, well, somewhat stabilized carbanion. And once that forms, it's still very, very basic. And look at what we've made. We've made a carboxylic acid. So what happens is a simple acid-base reaction. The CBr3 minus simply deprotonates the carboxylic acid to form a carboxylate. And that's a resonance-stabilized anion, way more stable than even the hydroxide would have been. And so it's a thermodynamic sink. Typically, the reaction is then quenched with a small amount of acid to protonate everything, and you wind up making a carboxylic acid and what's called a haloform. You're probably familiar with chloroform, which is CH-Cl3. Here we're using a bromoform as a product. A couple of interesting things about this reaction. If I'm not mistaken, I think this is the first reaction that you guys have seen that involves breaking a carbon-carbon sigma bond. If you think about it, the acetophenone starting material, the ketone, we're removing a carbon from the carbon skeleton. And that can be synthetically useful. Not nearly as useful as making carbon-carbon bonds, but sometimes it's actually a good thing to be able to do that. There's actually a little historical interest with this reaction as well. Back in the days before they had spectroscopy to determine structures of things, structures were determined using experimental methods, wet chemistry. The haloform reaction was actually used as a test for methyl ketones. The idea is pretty straightforward. You would react your mystery substance with an excess of either bromine or iodine, treat it with hydroxide, and if it formed a precipitate, it meant that it had undergone a haloform reaction because iodoform is in fact a yellow solid. So it was a simple test. If it didn't form that yellow solid, then you know it wasn't a methyl ketone, and only methyl ketones can undergo the haloform reaction. All right, so our next reaction's another quirky one. It's actually yet another variation on halogenation. And if you've ever thought that organic chemistry was hell, well, today you're actually right, because we're going to look at the Helffolard-Zielinski reaction. This is actually just an alpha-halogenation, but specifically on carboxylic acids. This is kind of nice because it really shows what a lot of this chapter, this unit, is all about. It's basically taking a lot of stuff we already know and then just expanding on it or putting it together in new ways. So here we've got a carboxylic acid. The conditions are to use something like PBr3 and bromine, and then an aqueous workup. Now, we already know what PBr3 is going to do to a carboxylic acid. That we talked about last unit in our acyl substitutions. That's simply going to make an acyl bromide. Now, once that acyl bromide is formed, it actually generates HBr, as a byproduct. That acid then forms an enol with our acyl bromide, allowing the halogenation to occur with the Br2 that's in there. In other words, it does an acid-promoted halogenation. After that, you treat it with water, and water simply hydrolyzes the acyl bromide back down to the carboxylic acid. It's really just a package of three things you've seen before. The initial step being the bromination of the carboxylic acid, which we saw in our unit on acyl substitutions, followed by an alpha halogenation under acidic conditions, which we just saw, well, last week, and then finally a hydrolysis of the acyl bromide back to the carboxylic acid, which again was just an acyl substitution we talked about in our last unit. All right, so from here, we're going to be looking at mostly, I think entirely, carbon-carbon bond-forming reactions. And the first one we're going to look at is alkylation. This is simply taking an enolizable carbonyl, I'm going to use acetone here, treating it with a base, and then an alkylating agent. An alkylating agent typically is something like an alkyl halide. Again, this is similar to what we've seen both with, say, Friedel-Crafts alkylation and with the acetylide anion. So we talked about on terminal alkynes last semester. In this case, we're going to use LDA as our base, and that's going to form a quantitative amount of the enolate. This is under basic conditions. So you can see the enolate, and then it's just going to do an SN2 reaction if you think about it, right? We know that enolates are nucleophilic on the alpha carbon. So what happens is a lone pair from the oxygen pushes down to form the pi bond, the carbonyl. That sort of expels out those pi electrons from the alkene, acting as a nucleophile, attacking, in this case, 1-bromopropane and displacing bromide in an SN2 reaction. Overall, you wind up introducing a propyl group in this case, and it just extends the carbon chain. We started off with a 3-carbon ketone, and now we've got, what is that, 6-carbon ketone. But mechanistically, it's just a combination of things we've seen before. It's just forming an enolate, which we saw a couple weeks ago, and then doing an SN2 reaction on it with an alkyl halide. Now, the conditions here are, in fact, critical. You notice that I used LDA here, and that's kind of what our uber base at this point, right? We talked about this a few days ago when we looked at how enolization can be influenced by the type of base you use. LDA being a very strong base is going to give you a quantitative 100% amount of enolization, and that's really going to be important, as you're going to see. I can't really tell you why right now, but when we look at a few more reactions, we'll be able to kind of go back and look at this, and you'll see why using LDA, using something, a base that's going to quantitatively deprotonate our ketone, our carbonyl, is really important. So a lot of times chemists refer to this as kinetic base. You need a really, really powerful base. It's actually a misnomer, but because we use really strong bases to sort of promote kinetic enolization, when you have that issue of regioselectivity, we often refer to it as kinetic base or kinetic conditions. But this is just a nice way of taking something like a ketone or an aldehyde or an ester and simply extending the carbon chain using an alkyl halide. All right, well, our next set of reactions I would say are probably the most heavily studied reactions, at least organic chemistry reactions of all time. These are the Aldol reactions. There's a couple of them. We're going to start off by talking about the Aldol Addition. So the Aldol Addition is a reaction between 2 carbonyl compounds. So here I've got a couple of molecules of acetaldehyde. We're going to use, again, LDA in this case, although that base can be changed. We'll talk about that a little bit later. And here I've written out the same molecule twice, if you notice, right? I've written acetaldehyde twice. Now, we're not normally going to do that, but I think it's really useful to be able to see both molecules when you're first learning this chemistry. So the idea is pretty straightforward. We have all of this carbonyl. We're going to enolize one of those two carbonyl molecules. No, they don't have to be the same molecule, but again, I'm trying to keep it simple here for this first example. So the LDA is going to form the enolate of one of those two carbonyls, an aldehyde in this case. And then that enolate is simply going to react with the other carbonyl. It's a nucleophile, right? And we know that carbonyls are electrophiles. In this case, I have an aldehyde, and we know that aldehydes undergo acyl addition. So the nucleophile, the enolate, is going to attack the carbonyl carbon, breaking that pi bond, and it's just going to hang there as an alkoxide until we add an external acid to protonate the alkoxide. In other words, again, this is just a combination of two things we've seen before. We already know how enolates are formed under basic conditions. We know that enolates are nucleophiles. And we know that aldehydes and ketones are electrophiles that do acyl addition. That's all this is. This is just an acyl addition with an enolate as the nucleophile. Go back in your notes and take a look at, say, the cyanohydrin reaction. If you pretend that this enolate on the right here is, in fact, say, cyanide, it's the exact same reaction mechanism, right? It's just acyl addition. This kind of chemistry does confound a lot of students because you end up taking two different functionalized molecules, in this case two aldehydes or ketones or whatever, and then reacting them together to join them into one carbon structure that also has multiple functional groups. And if you see, we made, in this case, a beta-hydroxycarbonyl. Again, starting from the carbonyl on the right, the alpha carbon, and then on the beta carbon, you have that hydroxy. A lot of times these are referred to as aldol products or aldol addition products, and that little structural motif is actually a really important one, both synthetically and biologically. So that's the aldol addition. Related to this is another aldol reaction called the aldol condensation. So here, I've got the exact same two aldehydes. Again, I'm just using these because they're fairly simple to draw out. And I'm using a different base here, but again, it's base. It's basic conditions. I'm using hydroxide here. So again, what we're going to do is the same thing we did up above. Some of that carbonyl is going to wind up getting enolized. Some of it is not. The ones that get enolized will then attack the ones that didn't get enolized. So you have a nucleophile enolate attacking the electrophilic carbonyl. It's just going to do an acyl addition. Specifically, it's going to do an aldol addition, right? Notice that the product here is exactly the same thing I made up above. It's that same beta-hydroxycarbonyl. The difference here is that I'm using a weaker base, and typically that's what you need to do to an aldol condensation. Once we've actually made the product, note that the product here, in fact, has alpha protons, and that means that the product can now be enolized as well. So those hydrogens are actually fairly acidic. And that hydroxide that we've got here can come along and remove one of those alpha hydrogens, making another enolate. But rather than using that as a nucleophile, what happens is the beta hydroxy group can now act as a nucleophile, as a leaving group. Essentially what happens is the lone pair on the oxygen drops back down, and instead of the carbon-carbon pi bond going and grabbing a nucleophile, it simply shifts over towards that beta carbon, which has an electron deficiency on it from the electronegative oxygen, forming a new alkene and expelling hydroxide out as a leaving group. That makes the final product an alkene, specifically an alpha-beta unsaturated carbonyl. And if you remember, we talked about alpha-beta unsaturated carbonyls and their importance with respect to conjugate additions in our last unit. This is actually a really common way of making alpha-beta unsaturated carbonyls, doing aldol condensation type chemistries. That sets you up to doing direct attack with further reactions or conjugate attack on further reactions. In other words, you have a molecule now that is electrophilic on two different carbons, the carbonyl carbon or the beta carbon. Again, you can either do direct attack or conjugate attack depending on the kind of molecule you have, the functional group, and the actual nucleophile involved. Now, the aldol condensation is typically performed under thermodynamic conditions, and the reason for that is pretty straightforward. If you go back to the aldol addition reaction, once the actual addition occurs, before the alkoxide is protonated, your intermediate is negatively charged on that oxygen, and it kind of just hangs there because it doesn't have the ability to expel a good leaving group. In other words, we don't have a hydroxide yet. So it just sort of hangs there until you quench the reaction, and at that point, there's no longer any base to promote the elimination of the water that we saw in the aldol condensation. So what having hydroxide does, rather than LDA, is the hydroxide can grab a proton and lose a proton and then come back and grab another proton. And it can equilibrate backwards and forwards. LDA, once it grabs a proton, it's not giving it back. But if hydroxide grabs a proton, becomes water, it can give it back somewhere else and then come back and get it again. It goes backwards and forwards. This allows the reaction to progress forward, even with technically a substoichiometric amount of hydroxide. All right, so most of the rest of this unit of material is going to be all about kind of variations on this aldol idea, making enolates from some carbonyl and then reacting it with other carbonyl species. We're going to look at a few variations on aldol, starting off with the mixed aldol. As I mentioned a little bit ago, whenever you make an aldol reaction go, it doesn't actually have to be the same carbonyl that you make the enolate out of that's also attacked as the electrophile. When you have a different carbonyl acting as the enolate and a different carbonyl acting as the electrophile, we call that a mixed or crossed aldol. So here I have an example where I'm using acetone and acetaldehyde. So let's say we did an aldol. It doesn't really matter if it's an aldol condensation or addition, but let's say we did an aldol. The problem with this reaction is that both of these carbonyls have alpha protons. And that means that either one of them could get enolized. And that means that you have the potential to make two different enolates, which then could each react with either of the unenolized original carbonyls. And in other words, you could make products by enolizing acetone and having it react with unenolized acetone, or you could enolize acetone and have it react with unenolized acetaldehyde, or you could enolize acetaldehyde and react it with acetone. You get the point. There's a lot of different products that are going to come out of this, and it's not a terribly useful reaction because of that. There's really no way to control which of these two molecules gets enolized if the base you're using is something like hydroxide. So this is not a very good reaction, but there are a couple of ways to kind of clean it up a little bit. One possible solution to this is to simply do the reaction where only one of the two carbonyls is in fact enolizable. In other words, only one of the two carbonyl compounds has alpha protons. This is really commonly done with things like benzaldehyde or substituted benzaldehydes. You see how on benzaldehyde, there's only one alpha carbon, and it's a benzene carbon, and it doesn't have any alpha hydrogens on it. Benzaldehyde can't form an enolate. So if you then react this as the electrophile with some carbonyl species that does have alpha protons that can be enolized, something like acetophenone, well then you know that's going to get enolized, and it limits the number of products that can form. And in this specific reaction, it's actually not so bad. It's still possible that acetophenone could partially enolize and then react with some of the unenolized acetophenone as well. But that's a ketone. And in the presence of an aldehyde, in this case benzaldehyde, we know that aldehydes are actually better electrophiles. They're more reactive than ketones. So since only acetophenone can make the enolate, and even once that forms, it has a choice, so to speak, between reacting with acetophenone as an electrophile or benzaldehyde, and aldehydes are more reactive, well, that means that it's going to attack benzaldehyde. And you get a fairly selective reaction this way. You'll note that in this case, I used hydroxide, and that's going to wind up doing an aldol condensation, excuse me. And it's a good reaction. In fact, this specific reaction is really good at making those condensed products because of the extra benzene ring on the left. By doing that elimination, by removing water, by going through the condensation and not just the addition, you have the ability to conjugate that benzene ring on the left to the rest of the pi system, the carbonyl and the other benzene ring, and that creates a lot of stability in the products. So it really forces this to go through the condensation rather than the addition. In fact, this reaction actually has a name. It's called the Claisen-Schmidt reaction, but I don't normally write that down because I don't want you to get confused with some other Claisen reactions we're going to look at a little bit later. So this is one solution, or one possible solution to this mixed aldol problem of making lots of different products. Of course, it is limited because, well, what if you don't want to make that product? what if you really did want to make a product specifically from, say, acetone and acetaldehyde? Well, then this solution isn't going to work. So the way they got around that about 30 or 40 years ago now was when we were starting to be able to make strong bases like LDA. And it's a really, really simple, elegant solution. But we needed strong bases that could completely quantitatively enolize a carbonyl. So here's how it works. You simply start off with one of your carbonyls that you want to enolize, treat it with LDA, and quantitatively enolize it so that every single molecule of that specific carbonyl, acetone in this case, gets enolized. Then that enolate is then reacted with the second carbonyl compound. Now, it can't get enolized because, well, you've already formed your enolate and there's no more base left over because you're using such a strong base. It's already gotten all those acetone molecules deprotonated. And again, once LDA grabs a proton, it's really not going to give it back because it's so, well, not acidic, the conjugate acid. So now the enolate forms from acetone and selectively can be reacted with, in this case, acetaldehyde. Once that occurs, it again hangs as the alkoxide. Go back and look at your notes on the Aldol Addition, and then we just quench it with an acid to put a proton onto that oxygen. This is a really powerful trick, but it wasn't possible until we had these sort of uber strong bases like LDA. If you tried to do this exact experiment, do this exact reaction with a weaker base like hydroxide, it wouldn't work. Because the acetone with hydroxide as the base would only get partially enolized. If you had 100 acetone molecules, only like 1 or 2 of them would get enolized. And that means that the other 99 of them would be sitting around to act as an electrophile with the enolate you just formed. In other words, it would do a normal aldol. It would just have acetone enolized and then react with acetone before you ever had a chance to add your second carbonyl. That quantitative enolization is critical, and that's why this really wasn't a thing until we introduced these kinds of strong bases that can completely enolize every single molecule that you're trying to enolize. All right, we've got one more variation on the aldol reaction, and that's simply the intramolecular variation of it. It's certainly possible to do an intramolecular aldol reaction, either condensation or addition. Now think about what an aldol reaction requires. You need a carbonyl that gets enolized, and then you need another carbonyl that doesn't get enolized to act as the electrophile. So for an intramolecular reaction, what you need is a dicarbonyl. So here I have a diketone. And I've kept this example fairly simple because I've made the ketone symmetric. Now, there still are some things to consider here. If you look at this carefully, hopefully you can see there are a lot of alpha hydrogens that we could deprotonate here. Specifically, there are 2 unique sets. The methyl hydrogens are all the same by symmetry, and so are those methylene, those CH2 hydrogens on the left, but they're unique from the methyl hydrogens. That means we can form 2 possible enolates here. So what happens? Well, you would think maybe it depends on the kind of base you use, right? We talked about thermodynamic versus kinetic control of enolizations. And that's true to an extent, but let's take a look at this from a slightly different perspective. Let's say we actually enolized and we were using hydroxide, a thermodynamic type base, a weaker base. That would prefer to make, under those equilibrium conditions, the more stable, more highly substituted enolate. That means we wind up removing one of the methylene hydrogens. Now, once that enolate forms, think about it. That enolate now needs to attack the other carbonyl of this molecule. And if that were to occur, reacting from, say, this lower methylene, attacking that upper carbonyl, it would form a bond between those 2 carbons and actually make a 3-membered ring, a cyclopropane. And we know that cyclopropanes are pretty unstable because of angle strain and torsional strain. Now look at the other alternative. What if we remove one of the hydrogens from one of those methyl groups, form the enolate that way, which technically is a kinetic enolate? Well, if one of those methyl carbons was deprotonated, that enolate could then attack the other carbonyl. That carbon-carbon bond would then close up a 5-membered ring, and that is, well, really stable, right? 5-membered rings have very little ring strain in them. So that's what actually occurs. Even if you use a thermodynamic base, this is a little weird, but think about it. Think about what thermodynamic control means. It just means that things can equilibrate. While the enolate that would form initially using a thermodynamic type base, a weaker base, would in fact be by deprotonating those methylene hydrogens, the more substituted, more stable alkene. The product it can form from that is going to be a three-membered ring. And that's so unstable that it's basically just going to pop back open again, reforming the enolate. But what can happen, of course, is you are going to form a small amount of the kinetic enolate, right? It's under equilibrium. You're always going to make a little bit of everything at the very least. And every time that methyl group gets deprotonated, it can then attack the other carbonyl and make a very stable five-membered ring. And that's basically what happens because the other alternative initially may be lower in energy. That is, the more substituted enolate is going to form. It leads to a crummy product. It leads to that three-membered ring, very strained product. Whereas enolization off the methyl carbon, while initially disfavored because it's a less stable enolate, ultimately proceeds into a much more stable five-membered ring. And of course, then you just either protonate the alkoxide that forms, or often you see when doing intramolecular aldols, especially with weaker bases, you see an awful lot of the condensation product. Now, intramolecular reactions are notorious for confounding students. I don't know what it is. I always joke, rings mess with people's heads. That's why I'm not married yet, right? But it's true. Ring systems do kind of mess with people, but just trace it out. In this example, what I've done is I've taken the hydrogen off of the top carbonyl's alpha methyl group, right? And simply attacked onto the carbonyl on the bottom. And then, of course, the alkoxide that formed would get protonated. After that, if you look, that CH2 that I've got drawn out here on the right next to the carbonyl, that can then get deprotonated again with our base, form the double bond by pushing the electrons towards that electron-deficient carbon with the hydroxide on it, and then expel the hydroxide, squirting off water, essentially, and giving us the condensation product. Again, look at that product, look at the condensation product. It is an alpha-beta unsaturated carbonyl as long as you look at it in the right direction, right? And of course, this is going to be a very doable reaction, this intramolecular variation of aldol chemistry, when you are making stable ring structures. Things like 5- and 6-membered rings are generally going to be preferred. You have to look at it that way, though. Just don't go and sort of have a knee-jerk response of, I have a thermodynamic base, I've got hydroxide, I'm going to form the thermodynamic enolate. You've got to look at what the products are going to be. And if you're making a really strained ring or even a very, very large ring that's going to be very hard to make, that's not what's going to happen. You're going to wind up making the most stable ring possible. You just have to figure out which side of the carbonyl is going to get enolized and what size ring would form from either enolization. And you just want to make the more stable ring size. So in this case, it was a choice between a 3-membered ring, which is terrible, or a 5-membered ring, which is actually quite stable. And again, it can be an addition product, it can be condensation, depending on the exact conditions, but ring systems like 5- and 6-membered rings are notorious for doing that elimination step, for eliminating the water and doing the condensation. So it often is seen. All right, I think that's going to wrap it up for this time. Next time, we'll start looking at how enolates can react with other kinds of carbonyl compounds, specifically the acid derivatives. And we'll see how enolates can actually undergo acyl substitution reactions.